All right, so I'll say it again. Working in a stockroom of a store, you are required to push a box across the room. The box has a mass of 100 kilograms. You push on the box with a horizontal force, but there is a frictional force acting on the box that is 60% of the normal force. With how much force do you have to push to get the box to slide at a constant velocity? So you all just said that this is a first law problem. All right, first law problem. Now that I know that, let's draw a free body diagram that describes the situation. So, dot here in the middle. Name a force that's acting on the box. Well, there's a lot. Which one do I want to put in there first? Weight or friction? Weight. So, weight downwards. All right, so it says you are pushing on the box with a horizontal force. And the box is resting on the ground. So, give me another force that's acting on the box. Normal force, okay. The box is resting on the ground, so the ground pushes up on the box. That seems reasonable. So the box is experiencing two forces, at least. Is there any other force acting on the box that we should know about? All right, so friction, that's fine, but friction is a force that opposes one surface from sliding across another. So is my box sliding to the left or sliding to the right? Okay, if the box is sliding to the right, that means friction must be to the left. So I'll draw a force to indicate friction is acting to the left. It says that friction is 60% of the normal, so I'm drawing it smaller. This looks unbalanced to me. Is there anything else acting on the box? Us pushing it. What direction do we push? Right. We want to make the system look balanced. So we're pushing on the box. I'm going to call this F with a P for pushing. There we go. Does this look balanced to you? Looks pretty balanced to me. It's a net force equals 0 problem, so it doesn't matter what direction I draw in my coordinate system. I can draw it any direction I'd like. So I'm going to draw it in a direction that's easiest for me to solve. So how about that way for the x direction? And this way for the y direction? Is there more that we know what to do from this point? I mean, what other things can we do now? Nate, what's another thing we could do now? What's another thing we could do now?
Can we start solving for forces?
Sure, let's do that. Break this up into the net force in the x direction, which equals 0, and net force in the y direction, which equals 0. The mass of the box is 100 kilograms. So weight is, how do I calculate weight?
Mass times gravity.
All right, mg, mass times gravity, so that'll be 100 kilograms times 10 meters per second squared. That's got to be 1,000 newtons. That is the weight. I don't know what to do with it yet, but I do know that normal minus weight equals 0. Do you guys see why I know that? Net force in the y direction is 0. Those are the two in the y direction. That suggests that normal equals the weight. So normal is 1,000 newtons. Any questions? Any revelations here? All right. I know the pushing force minus the friction equals 0. But they want me first to figure out with how much force do I have to push to get the box to slide at a constant velocity. So they want this. I can't figure that out unless I know the frictional force. Is there anything about the frictional force that I do know?
60% of the normal force.
It's 60% of the normal force. They tell me in the problem that friction is of the normal force, which means 0.6 times 1,000, or 600 newtons. That suggests that my pushing force is 600 newtons. Yes, I think you know how to do your homework. Okay? I do believe you have skills. You'll need more skills. You have some skills. We're going to learn some more skills today, okay? We added the mass to the spring, and the mass stretched. That's a displacement, so I'll write delta x there. And the system was brought into equilibrium. That's a word that I'd like you to know. Equilibrium means everything's balanced. So if I say a problem is in equilibrium, it means the net force is 0. It means the acceleration is 0. It can be moving, bless you, but it can't be accelerating. So the word equilibrium means net force is 0 and acceleration is 0. This system is in equilibrium, so net force equals 0. You made it pretty clear that there are only two forces acting on it, an upward force, tension, and a downward force, weight. That's what's going on. There we go. So, weight and tension. These are balanced, so tension minus weight equals 0. But I'm pretty sure you guys saw something pretty clear, right? This is an interesting kind of tension in that the spring had to stretch in order to apply the proper tension. Did you notice that? Let me examine. What I mean is that there are what's called linear springs and there are nonlinear springs. Linear springs obey Hooke's law. Okay, linear springs obey Hooke's law. And I know that that's going to be challenging for us because you don't really know what I mean by linear, but I think you do know it. So mathematically, of course, this is physics. So there's got to be a way for us to express this that makes it all so much more complicated, right? Because that's what physics is about. So let me see. Force of a spring equals, it's linear. So something times how much the spring stretches. Right, that's linear, right? If I double how much force is on it, I double how much the spring stretches. You follow along? I just need to have a letter there. In your world, y equals mx plus b, you might put an m there, but this is physics, so we do have a symbol that we put there. And the symbol is really complicated. We use something called the spring constant, AK. We put a lowercase k. That is the spring constant. Yeah, k for what's that? I know, but we used a K here. I guess the guy who's doing it just didn't understand. He played a lot of Mortal Kombat too, and that's K for anything that's supposed to be a C sound. Now, there's more to this, and it's subtle. You won't believe this or you won't like this, but remember, force is a vector, so I put the bar on it. And displacement is a vector, so I got to put the bar on it. So you'll notice the spring stretched down, but the force was up, right? So I got to put a negative sign out front. That way I make sure I deal with the fact that there's direction there. All right? Now, here's what I want you to tell me. I want you to tell me what the spring constant is for the spring at the front of the room. And I know you're thinking, Mr. Shelton, I don't know how to do that. You've never shown me this before. I think you can. Ready? Let's do what we know. We've gotten this far so far, right? I said to you that we're hanging 200 grams. So the mass is 200 grams. How many kilograms is that? Who doesn't know how to do this? It's okay if you don't know. All right, kilo is 1,000. So we have to divide by 1,000. So it's going to be 0.2. Yeah, well, physics was yesterday. All right, so 0.2 kilograms. I'm bringing this up because you guys know that weight is mg. Seems to me you can figure out the tension because you know weight is mg. So tension is mass, 0.2, times g, which is 10. Seems like the tension in the spring is 2 newtons. I know, you said, Mr. Sheldon, I don't know how to do any of this, but I'm telling you, you do. You know a lot more than you think. The tension in a spring comes from a spring, right? Which means the force on the spring is 2 newtons. Equals minus k times, how far did the spring stretch? What did I say? Well, it's actually 9.5 centimeters. I want to be honest. 9.5 centimeters. But newtons has meters in it, so I don't want to use centimeters. I want to use meters. So it stretched 9.5 centimeters. How many meters is that? 0.095. Excellent work. So we'll put that 0.095 there. However, did it stretch upwards or downwards? Downwards, but I put a negative sign there. Right? We've got to make sure direction. That's important. Alrighty, you can tell me K. You guys are smart people. Do so. Tell me K. 21. We'll just say 21. That's okay, right?
Yeah.
Units here are important. 21 newtons divided by meters. That's the unit of the spring constant, newtons per meter. It can be reduced, but this is good enough. Leave it like this. It tells you how many newtons you get for every meter of stretching. Do you see how it sounds like a spring constant? How many newtons you get for every meter of stretching. This is a weak spring. Let me ask you this. Do you think the springs in your car have a higher spring constant or a lower spring constant? When you sit in your car, does it sink down a lot? I hope not. You've been eating a lot of dense food or your springs need to be replaced. So I'd argue that your car does not sink as much as that weight sunk, right? It probably just sinks a little bit. So when we talk about this, a big spring constant, this is not. So I'm going to draw a little picture here, but you guys draw a free body diagram for the calculator. So calculator, which is just chilling. That's right. Cover of book. All right, there we go. That's what we have, right? You're drawing a picture. Is this a first law problem or a second law problem? So net force equals 0. Reduce all the forces on the object to a dot, or all the mass to a dot. Go down my list. Is there any fundamental force acting on the calculator? Gravity. So I'm gonna draw a downwards arrow to indicate gravity. Don't add forces to this. Let's try and just make sure we are following our set of steps. A lot of you guys will try and veer off and find new things. There we go. Is there anything in contact with the calculator? Book. So I need to draw what kind of force? What would we call this force? Normal forces. Normal forces are perpendicular to the surface in contact. That means perpendicular to the book. So I'm going to draw an arrow over here. Does that look perpendicular to the book?
No. Oh, yeah.
I think so.
Yeah, it does.
Thank you.
How about this?
So I'm going to draw it over there. That look good now? All right. Does that look balanced?
No.
Now I want to point out, so if you're going to draw friction, we're going to say friction is what's holding it in place. It's preventing one surface from sliding past the other. Fine, draw in a frictional force, but the frictional force has to be parallel to the surface. So I'm drawing the arrow so that I know it's parallel to the surface, and I'm going to take that sucker over here. There we go. Now that looks balanced to me. For every left, I see a right. For every up, I see a down. Do you guys see that too? Now, if we're going to analyze this, and I'd like to, it's not moving, so we can choose any coordinate system we like. Right? Any coordinate system we like. So we could choose a coordinate system that's aligned with gravity. That tends to be what you guys like because it's up and down and straight, and those things tend to make you feel happy about yourself. So we could do this. But if we do so, do you realize that two of our forces are off axis? We have to do two sets of all that geometry stuff. So would you have a problem with just tilting this so that it's not like that, so that it's lined up with maybe this one? Because if it's lined up like that, then the y direction will have to line up with that one. Because, and I'll repeat, normal force and friction have to be perpendicular to each other. God, you guys yawn a lot. You guys are young, full of energy. Yeah, I'm not yawning, I'm old man. I am having the worst tea in the planet. It's just herbal garbage tea. I guarantee you, I haven't had any caffeine since this morning. It's terrible.
There's no source of energy in that tea.
There is no, it's taking my energy away a little bit with my soul.
Oh. Oh.
So, all right.
Are you supposed to get like that thing and like get your coffee machine back?
I have a coffee machine. I broke my other coffee machine. My French press broke.
Is it expensive?
No, they're not expensive. It just broke. I just haven't bought. I have a Keurig. It's in the back of the room.
I thought it's like you make espresso.
I'm not supposed to be making coffee. My family says no. All right, look. I want to finish. I got 4 minutes. You're going to give me 3 minutes. You're going to give me my 3 minutes. Look, let's say that this angle is theta here. Where do you think that goes over there? Does it go here or does it go here? Remember, this is the normal force. This is friction. This is weight. This one's tough. Now, look. I tried to make this as cleanly taken from the picture as possible. Would you agree? If I make the angle of the book smaller, the normal force is going to tip upwards, right? Like if I bring the cover down, isn't the normal force going to tip more upwards? So if this angle gets smaller, which of these two gets smaller, A or B? A. So A is where theta goes. If you don't want to memorize that or figure it out every time, then I will tell you, theta is the angle between the weight and a line drawn through the normal force. Theta, for the incline, will also be the angle between the weight and a line drawn through the normal force. If you don't want to figure it out, that's what you should do. Now, I'm going to point something out, and I'm going to run out of time doing so, but the off-axis force is the weight. That suggests I'm going to have to put a component this way and a component this way. Not that way, this way. But look at me, folks. You're going to do this, and if you're the person who does this, I'm going to hang your test on the wall. You're going to do something like this. One of you is going to do it. You're going to make your components look like that, and I will forever make fun of you. Remember, components must be perpendicular to each other. So the right angle goes here. And by the way, I know you're trying to pack up, but I'm going to give you something super valuable right now. Which side is opposite? A or B? B is the opposite side, so that's going to be the sine. Weight sine theta. That makes A the adjacent side, which is going to be weight cosine theta. An incline is going to look like this, with net force in the x direction equaling something and net force in the y direction equaling something. There can be accelerations and such, but down the ramp will be weight sine theta. And into the ramp will be weight cosine theta. Sometimes there'll be friction too, just like we have on this one. In this problem, both of these equal 0. But inclined plane problems are a big deal in AP Physics. They show up all the time. Figuring out where you put weight sine theta and weight cosine theta is going to be important for you. Alrighty.